Hello there, I'm Shomit Ghose, and we're here today to provide a satellite-level view over the field of generative AI and the many ways that it can have an impact on enterprise applications. And I'll add that all the applications we'll touch on today are independent of large language models, which are also known as LLMs. Specifically, we'll discuss how generative AI impacts the enterprise in application areas that have nothing to do with generative chat. Almost 50% of 4,700 CEOs surveyed foresaw existential risk to their business in the coming 10 years due to the impact of AI. This begs the question of how C-level executives today should plan for this AI-driven future. How should they view and harness the opportunities that AI brings? If we don't have a clear view of what AI, specifically generative AI, is, we cannot hope to leverage its capabilities to improve our businesses. OpenAI has a tremendously cool one, and Google's Gemini is equally capable. There are many others out there for you to use, and all of them are quite powerful productivity tools. But you may not know that what makes the Gen AI chatbot applications work is an underlying engine known as the Transformer, which was invented by Google back in 2017. The really big breakthrough in AI was the T in GPT, the Transformer. We tend to view Gen AI's impact on the enterprise through the lens of generative chat, through applications like ChatGPT, but if you blow away the cloud, what you see is that generative AI is a broad set of technologies, one of which is the Transformer, and it's these technologies that support higher-level vertical applications such as generative chat. Transformers are a powerful method in Gen AI, and there are quite a few other Gen AI technologies out there, including Diffusion and GANs, all of which support impactful enterprise applications. We'll touch on a few of these today to give you a flavor. And beneath the various Gen AI models are many different enabling technologies, both within the hardware and the software. These enabling technologies help make Gen AI computationally efficient, but we'll leave the discussion of these enabling technologies to another day. So what's a transformer? A transformer can be thought of as a processing engine that helps solve the problem of language interpretation, and more importantly, can be applied to interpreting anything that includes data in sequence. When you consider natural language, it's a long sequence of data, words arranged in sentences, within paragraphs, etc. Importantly, language encodes meaning both through the meaning of the words themselves and also through the position of those words within sentences. Think about a collection of words like Joe ate the chicken. You can rearrange these same words to the chicken ate Joe and completely change the sentence's meaning. So language is a function of both the meaning of individual words, that is the value of the data element, and also the position of the word within the sentence. Understanding language is a function of both space, that is meaning, and time, that is positionality. And of course, language comes to us in high volume, so wouldn't it be great to be able to interpret all the words in a sentence in parallel? This is exactly what a transformer does. So this is the problem that Google solved through its invention of the transformer. We're all familiar with the joke of, why did the chicken cross the road? What if the answer was, the chicken did not cross the road because it was too wide? When you encounter the word it in this sentence, does it refer to the road being too wide or the chicken? Of course, we understand that the road was too wide, but prior to the invention of the transformer, traditional natural language processing technologies had a hard time figuring out what the word it referred to, the chicken or the road. Here's a simplified diagram of the transformer neural network. It's a mechanism for accepting sequenced input, where data positionality matters, you'll see that in the bottom left-hand corner, and producing sequenced output, where once again, positionality matters, as you see in the top right-hand corner. We can see how text or prompts can be input at one end of the transformer, and the statistical mechanisms produce coherent output at the other end. This is how applications such as ChatGPT and Gemini produce all of that wonderful text. Needless to say, there are many enterprise applications that feature sequenced data where positionality matters. The very same transformer that produces poetry via ChatGPT can also be used to predict health state for individuals, inputting electronic health records at one end and using the transformer statistical mechanisms to output future disease states at the other end. Transformers can also be used to classify cyber threats. They can even be used to design drugs, inputting amino acid sequences at one end and predicting protein bindings at the other. We should be sure to point out once again that the transformer applications such as drug design are independent of underlying large language models. They have nothing to do with large language models. You may also be interested to know that Meta's music generation application is also built upon the transformer. In music, we have notes, and the positionality of notes relative to other notes matters if we're to have actual melodies and not random noise. Now, the most recent flavor of generative AI that's breaking upon us is image generation. The consumer applications of this seem to be all around us today. One of the ways to generate de novo images is through a generative AI technology known as diffusion. Diffusion leverages a concept from thermodynamics. Basically, it's a process of adding noise to a data set, for example, an image, until you've essentially converted the data set to maximum entropy and apparently nothing but noise. The noising functions used in diffusion, however, are invertible, which allows you to take a data set that's seemingly 100% noise and run the noising functions in reverse as a denoising function and generate something that's brand new. It takes a little to get your head around this concept, but diffusion turns out to be a tremendously powerful generative AI technology. One of the ways in which diffusion generative AI has been used is in drug design. The goal in drug design, of course, is to find protein ligand bindings so that you can change protein behavior. Using diffusion, valid protein ligand bindings are diffused to maximum entropy using a noising function. This enables you to, when presented with a novel protein, run the noising functions in reverse to generate novel ligand bindings. The results of applying diffusion generative AI in drug design have been very promising, as you can see here. This will likely be one of the most impactful generative AI technologies within the pharmaceutical industry. Here's another application for diffusion Gen AI, weather forecasting. Needless to say, accurate weather forecasting is a huge need in many verticals, including agriculture, energy, logistics, and travel, to name but a few. How might we use generative AI within these verticals? Perhaps by doing weather forecasting using diffusion. Here's one more generative AI technology that's pretty interesting. It's called the Variational Autoencoder, also known as VAEs. VAEs are yet another technique for capturing data distributions, and their impact have been felt in everything from traffic prediction to music generation to crafting financial trading strategies. Yet another and final for today, super powerful Gen AI model that we'll touch on is the Generative Adversarial Network, also known as the GAN. GANs use an adversarial technique to model data distributions. Once again, no large language model is required, and GANs' enterprise use cases extend from image generation to the manufacturing floor to traffic simulation to drug design. In fact, there's a lung cancer drug now in human clinical trials that was designed using a GAN. In the field of medicine, we can foresee that Gen AI will be used to help capture doctors' notes, but using GANs to design life-saving drugs is likely an even more impactful enterprise use case for generative AI. As with all technology, there are pitfalls within generative AI, and these pitfalls are many, principally tracing their origin to suboptimal data substrates. Let's just highlight one, which is very illustrative. This was work that was done using generative AI and producing toxic results, and was work that was done at Carnegie Mellon University a few years ago. Researchers there used GPT not to generate the next word of text, but to generate the next pixel in an image. When the researchers fed in headshots of males and females, about 43% of the male images were rendered wearing suits or career-specific attire, while about 53% of the female images were generated wearing low-cut tops or bikinis. In other words, garbage data in produces an inevitable garbage data out. AI is 100% data-driven. If that data is unrepresentative of the real-life data distribution, we will get results that are damaging. The risks within AI from low-quality data are therefore quite profound and require scrutiny and careful thought, constant paranoia. The goal today was to give a quick snapshot of the many different ways of doing generative AI and the many, many different business applications these deliver. and also inject a small note of caution of the dangers that AI can also bring. So when you see a consumer application such as ChatGPT or image generation or music generation coming from one of the big tech players, this is a very powerful technology proof point. But realize that this generative AI technology can and will be generalized to solve a broader class of enterprise problems. Big tech understands this quite well. They don't view generative AI as being solely a tool of delivering consumer applications. You too must understand this. Thank you very much. A couple of readings here which you may find of interest.